We continue our look at infinite series. Specifically, we will look at another example using the direct comparison test, part 2. Let's quickly recall that the direct comparison test, part 2, states that if there's an integer n and our series terms are arranged such that b sub n is smaller than a sub n, if b sub n diverges, then a sub n also diverges. Pictorially, if b sub n is smaller than a sub n, so we think of a smaller circle and a sub n being a larger circle on the outside, then if b sub n diverges or explodes, diverging to infinity, it takes with it a sub n, right? So it's getting bigger and bigger, and it takes with it a sub n, and therefore a sub n also diverges. That was the idea. So let's talk about our next example. Example number 4. Use the direct comparison test to show that the following series diverges. This time we take a look at the infinite series n equals 2 to infinity of the natural log of n over n. That is, n equals 2 to infinity of the natural log of n over n is our series that we call a sub n. We are looking for a series b sub n to compare to. This one's a little tricky again. We had an example earlier with the cosine of n over n squared, while this one has another transcendental function, the natural log of n over n. So let's start with a statement that is a fact. This is always true. So long as n is bigger than e, we can make the following statement. 1 will always be less than or equal to the natural log of n, which is less than or equal to n. This is a true statement, and in fact, this is one of those things that you want to kind of commit to your memory. Keep it somewhere in your notes. This is a statement that you often use when you're looking at direct comparison test that compares series that involve a natural logarithm. So write this down, keep this in mind, and this is a true fact. And you can see it visually. Visually, if we were to look at the graphs of these functions, here we have some value e, right? And here we have 1. And what happens is the natural log function does this right here, right? So here's the natural log of x. So if I have y equals the natural log of x, I have a certain function. And if I have y equal to 1, and then I have y equal to x. So visually, what happens is that when you are larger than e, the arrangement is that y equals 1 is smaller than the natural log function, which is smaller than the function y equal x. Or in other words, 1 will be smaller than the natural log of n, will be smaller than n. Okay, so that was just a little diversion. Let's get back to what we were doing. We were trying to find a series b sub n to compare to. So we're starting with an inequality that we know. 1 is less than or equal to the natural log of n is less than or equal to n. I want to get the original series I have, which is the natural log of n over n. So why don't we just divide each term in this 3-part inequality, or each part in this 3-part inequality by n? N's a positive number, so I can divide all the parts and I remain in the same order as far as the inequality symbols go. In other words, 1 over n will be less than or equal to the natural log of n over n, which is less than or equal to 1. The natural log of n over n is my original a sub n, the nth term in my original series. I think that means that we want to choose b sub n to be the series that corresponds to 1 over n. In other words, I'm going to select b sub n to be the series 1 over n. Why? Because I know what that series does. What kind of series is this? This is our harmonic series, remember? This is our harmonic series. And what does our harmonic series do? It diverges. And so, let's get our picture going. So, if we have a series b sub n that is smaller, so he's inside, he's smaller than another series a sub n, so a sub n is larger than it. And we know for a fact that b sub n is a series that diverges. That tells us, by consequence of the direct comparison test, that a sub n must also diverge. So, the conclusion works for us. Let's write it down. We have that we are going to let b sub n be the series n equals 2 to infinity of 1 over n. This is the harmonic series that diverges. So we have the series 1 over n, which is the harmonic series that diverges. In addition, we have an order such that the terms in the harmonic series are smaller than the terms in the original series. And therefore, because that harmonic series diverges, we have that our original series n equals 2 to infinity of the natural log of n over n also diverges. And it does so because of the direct comparison test. See, not as hard as you think. Do, though, make sure as I leave that you put this little inequality statement in your notes, because it becomes very helpful again when we talk about using the direct comparison test with with infinite series involving the natural log function.